In this video, I'm going to show you how to solve the ALEKS problem called calculating the mass of an electrolysis product from the applied current. I looked through quite a few versions of this problem and they all look like they are the exact same format, which is cool. This problem isn't as bad as it looks. Like, it looks pretty intimidating, but it's not that bad. There's one equation that we're going to use to solve this problem. That equation is A equals C over S, and in this equation, the A represents amps, and the C represents coulombs, and then S is seconds. And that is just the definition of, I don't even know if it's an equation, it's the definition of an amp. To solve this problem, we're also going to be using Faraday's constant, which says that there are 96,485 coulombs involved with every exchange of 1 mole of electrons in an electrolysis reaction. So this problem is going to give you the amps, and I didn't see any weird units, so it's going to give you the amps, and it's also going to give you time, and I didn't see anything other than units of seconds. And that doesn't mean ALEKS might throw like a milliamp in there, or it might have minutes in there. Just make sure that if you do have funky units for your amperage and your time, make sure you convert that into just straight up amps, not milliamps, and convert your time into seconds. ALEKS is also going to be asking you, or the problem is asking you, to calculate the mass of a particular metal that is being deposited on one of the electrodes in an electrolytic cell. I've been asked about lead specifically, and then it's asking me to think about the lead that's being deposited on the cathode. And so we also have 2 ionic compounds in this problem. I have PbSO4 and I have PbO. And what I want to do is make sure that I'm finding the ionic compound that matches up with the electrode that ALEKS is asking me to focus on. So I'm being asked to focus on the cathode, and the cathode is the one that involves the PbSO4. So that's the one that I want to pay attention to. The other ionic compound, PbO, that one is taking place at the anode, and again, my problem is asking me to focus on the cathode. So once I've identified which ionic compound I should be paying attention to, the next thing that I want to do is figure out the charge on the metal ion in this ionic compound. So I have PbSO4, and then I know that that is the polyatomic ion sulfate, which has a -2 charge, and that allows me to calculate the charge on this particular lead ion. It is crucial that you get the charge correct. So whatever you need to do to figure out the charge of the anion, whether that means you've got to look that up in a table of polyatomic ions, or check your periodic table if you have something that's more simple than that, you've got to get this charge correct. Once you know the charge on that particular ion, you're going to write a half reaction to show how that ion gets converted into the metal that ALEKS is asking you about. And specifically, what you need to do is just know how many electrons are required for that conversion from the ion to the atom. And then for mine, it is 2 electrons. And you're not going to be able to get this problem right if you don't get the correct number of electrons here. So once you've got all that figured out, you're ready to actually start solving the problem. And what we are going to do is use this relationship right here to calculate the coulombs that are associated with our provided amps and time. And then once we know how many coulombs are associated with that amperage at that time, we're going to use that to calculate moles, which will ultimately be converting into grams. So this equation, A equals C over S, we can rewrite that equation as A times S equals C, and we're going to use it in that form. The amps times the time is equal to the coulombs. The amperage is 26. Mine is 26, and I have 50 seconds, and that is 1,300 amps seconds, which is the same as a coulomb. That's the definition of a coulomb. And then what I'm going to do next is use Faraday's constant to convert my coulombs into moles of electrons. So here is my relationship right here. Now notice the conversion that I'm trying to do here, I want my Coulomb unit to be on the bottom of this conversion factor, and I want moles of electrons to be up top. So I am going to have to flip-flop this conversion factor in order for it to work for me. 96,485 needs to go down on the bottom, and then that's going to let me cancel out those units of coulombs. Once I've got that figured out, then the next thing that I want to do is a stoichiometric relationship between the moles of electrons and the moles of the metal in that half reaction that I wrote. So in that half reaction, I have 2 moles of electrons for every 1 mole of lead, and that's going to cancel out my moles of electrons. And then last but not least, the last step in this problem is actually calculating the mass of that metal. I have lead, and lead has a mass of 207.2 grams per mole. So that's my last step. And then I can just finish this calculation. 1,300 divided by 96,485 divided by 2 times 207.2. That gives me a mass of 1.3959 grams of lead. And it says 3 sig figs, so that's going to be 1.40 grams. It says that all that we need is the unit symbol, so we're not going to need to include that PB symbol on there. And that's all you have to do.